High in the mountains, water begins one of the most powerful journeys in nature. Snow melts, rain falls, and natural springs emerge from the rocks, creating streams that eventually supply towns and villages far below. At first, it may seem like gravity does all the work. Since the water is already at a higher elevation, it simply flows downhill without needing electric pumps. But hidden inside this seemingly simple system is a serious engineering challenge. The same gravity that moves water for free can also create enormous pressure, enough to burst pipes, damage valves, destroy storage tanks, and even shut down an entire water supply network. That is why engineers install a special structure along the pipeline called a pressure reduction chamber, a system designed to control the force of moving water before it becomes destructive. To understand why this structure is necessary, imagine a spring located hundreds of meters above a village. Water leaves the mountain and immediately begins accelerating downhill. As it loses elevation, gravity continuously pulls it toward lower ground. The farther the water travels downward, the greater the pressure inside the pipeline becomes. This increase is not caused by pumps or motors. It happens simply because of the difference in height between the water source and the community below. Many people assume that more pressure is always better because it means stronger water flow. In reality, every pipe has a pressure limit. Water pipes are designed to operate safely within a certain range. If the pressure becomes too high, the walls of the pipe experience enormous internal stress. Small joints may begin leaking, rubber seals can fail, metal fittings may crack, and plastic pipes can deform or even rupture completely. A single burst pipe can interrupt water service for hundreds or even thousands of people. The problem becomes even more dangerous when the water is moving at high speed. Fast-moving water carries a large amount of kinetic energy. If a valve suddenly closes or the flow changes direction rapidly, the moving water has nowhere to go. Instead of stopping instantly, it creates a powerful pressure wave that travels through the pipeline. Engineers call this phenomenon water hammer. The pressure surge can be many times greater than the normal operating pressure, placing tremendous stress on every component of the water distribution system. In mountain water supply systems, both problems often occur together. Gravity continuously increases pressure as the water descends, while sudden operational changes can generate pressure shocks capable of damaging the entire pipeline. Simply installing stronger pipes is usually not the most practical solution, because stronger pipes are significantly more expensive, heavier to transport into mountainous regions, and more difficult to install. Instead, engineers choose a smarter approach. Rather than allowing pressure to build continuously along the entire pipeline, they reduce it at carefully selected locations before it reaches dangerous levels. This is where the pressure reduction chamber becomes essential. Although it may appear to be a simple concrete structure built beside the pipeline, it performs one of the most important safety functions in the entire water supply system. Its purpose is not to stop the flow of water. Instead, it carefully reduces excess pressure while allowing water to continue moving toward the community below. As water enters the chamber, the flow conditions begin changing immediately. Instead of remaining inside a narrow pressurized pipe, the water often enters a larger enclosed space where its velocity decreases. Because the flow slows down, part of its kinetic energy is naturally dissipated. In many designs, turbulence develops inside the chamber, breaking up some of the energy carried by the fast-moving water. Although turbulence usually reduces efficiency in many engineering systems, here it serves a useful purpose by helping remove excess energy from the flow. Some pressure reduction chambers use specially designed baffles or internal walls. These structures force the water to change direction several times before leaving the chamber. Every change in direction causes the moving water to lose a small amount of energy through friction and turbulence. Step by step, the water becomes calmer before re-entering the pipeline. Other systems rely on pressure-reducing valves installed inside or near the chamber. These valves automatically adjust themselves according to upstream and downstream pressure. When incoming pressure becomes too high, the valve partially restricts the flow, lowering the pressure to a safe level before the water continues downstream. If pressure later decreases, the valve opens further, maintaining a stable operating condition without requiring constant manual adjustment. The reduction chamber also plays an important role in protecting the entire distribution network from sudden pressure fluctuations. Water demand changes constantly throughout the day. Early in the morning, thousands of people may begin using water almost simultaneously. During the night, demand often drops dramatically. These changing flow conditions create pressure variations throughout the system. By absorbing and regulating these fluctuations, the chamber helps maintain much more stable operating conditions. Another important benefit is protecting valves, meters, storage tanks, and household plumbing. Many of these components are designed for moderate operating pressures. Without pressure regulation, the high pressure generated by mountain elevation could shorten their lifespan considerably. Faucets may wear out more quickly, washing machine hoses could fail, and water heaters might experience unnecessary stress. Controlling pressure improves the reliability of the entire network, not just the main pipeline. The location of the pressure reduction chamber is carefully chosen during the design stage. Engineers study the elevation profile of the mountain, calculate expected pressure levels, estimate daily water demand, and identify sections where pressure would exceed safe operating limits. Large mountain water systems often include multiple pressure reduction chambers positioned at different elevations rather than relying on a single chamber near the bottom of the pipeline. Inside the chamber, engineers also consider air management. Air trapped inside a pressurized water pipeline can create operational problems. Air pockets may reduce flow efficiency, produce irregular pressure conditions, or contribute to pressure surges. Some pressure reduction chambers include air release valves that automatically remove accumulated air, while preventing outside air from entering the system when pressure changes. Maintenance is another important aspect of the design. Because these chambers are built in remote mountain environments, they must remain reliable for many years, with relatively simple maintenance procedures. Concrete structures provide durability against weather, while access covers allow technicians to inspect valves, clean sediment, and verify proper operation without excavating the pipeline. Although the chamber itself contains no electric motor, it performs a highly sophisticated engineering task using basic principles of fluid mechanics. It manages energy rather than creating it. The water still travels downhill under the force of gravity, but the excess energy is controlled before it can damage the infrastructure. Modern water distribution systems often include pressure sensors connected to remote monitoring equipment. These sensors continuously measure conditions throughout the pipeline. If pressure rises beyond acceptable limits, operators can receive alerts immediately. In some advanced installations, automated control valves respond in real time, adjusting pressure without requiring personnel to visit the site. Climate also influences the operation of mountain water systems. During periods of heavy rainfall or rapid snowmelt, the amount of water entering the pipeline may increase substantially. Greater flow can produce different pressure conditions than those experienced during dry seasons. Well-designed pressure reduction systems are capable of operating safely across a wide range of flow rates, ensuring reliable water delivery throughout the year. One common misconception is that pressure reduction chambers waste water. In reality, the goal is not to remove water from the system, but to remove excess pressure. The same volume of water continues toward homes, schools, hospitals, and businesses. The difference is that it arrives under controlled conditions that protect both the infrastructure and the people who depend on it. These chambers are especially important in mountainous regions, where communities may be separated by large differences in elevation. Without proper pressure management, the lowest sections of the pipeline could experience pressures several times greater than those near the source. By dividing the elevation into manageable pressure zones, engineers ensure that every section of the network operates within safe design limits. Pressure control also reduces long-term maintenance costs. Water utilities spend significant amounts of money repairing leaks, replacing damaged pipes, and responding to emergency failures. Stable pressure reduces mechanical stress throughout the network, extending the service life of pipes, valves, pumps, and household plumbing. Even small reductions in operating pressure can dramatically decrease the number of leaks over many years. The science behind the system is surprisingly simple. Gravity continuously converts elevation into pressure as water moves downhill. Left uncontrolled, that pressure keeps increasing until it threatens the infrastructure itself. Instead of fighting gravity, engineers work with it. They allow gravity to transport the water while strategically removing only the excess energy that could become destructive. Imagine standing beside a mountain pipeline carrying crystal-clear spring water toward a village below. Inside the pipe, the water is accelerating under the force of gravity. Without intervention, the pressure would continue rising until the system eventually failed. But before reaching that point, the water enters a quiet concrete chamber. Inside, its speed decreases, turbulence absorbs part of its energy, valves regulate the pressure, and the flow becomes stable once again. Moments later, the water continues its journey toward homes, schools, and farms, still moving entirely under the force of gravity, but now at a pressure the entire network can safely handle. That simple structure hidden along the mountainside rarely attracts attention, yet it silently protects thousands of meters of pipeline every hour of every day. Without it, gravity would become the system's greatest enemy. With it, gravity becomes one of the most reliable and efficient ways to deliver clean water to communities below. That is how mountain water pressure is controlled before it destroys pipes.